It is time to introduce Heisenberg's uncertainty principle, which you've probably already heard of. Its most famous incarnation is the position momentum uncertainty delta x delta p is larger than or equal to h bar over 2. In school, I was often told stuff like, if you try to measure the position of a particle using a laser, then it gets more precise if you use shorter wavelength, but then it also carries more momentum and thus pushes the particle around more. Now, while this is true, it didn't feel very fundamental to me. Indeed, when Heisenberg published his result, many experimentalists were offended, thinking that he stated that their method of measuring was somehow insufficient. So here I'm going to give you a mathematical proof that has nothing to do with the method of measurement, nor even the position or momentum, nor even particles. The path there is a bit more involved, but the result is much more powerful. First, we need to define uncertainty. I will use the statistical definition of the standard deviation of a measurable quantity, which is the square root of the expectation value of the difference between the corresponding operator and its expectation value squared. Man, I'm so glad I have mathematical formulae to show. Describing them in words is so clumsy. This expectation value, of course, depends on the wave function the system is in, but just to ease the notation a bit, I will not always include it explicitly. Because A is Hermitian, this expression can also be interpreted as the square root of the norm of the vector found by applying A minus the expectation value of A to psi. Let's call this wave function cat delta A. The left side of Heisenberg's uncertainty relation is given by the product of the uncertainties of two measurable quantities, represented by the operators A and B. Now we'd like to find an inequality for this expression. Consider two normalized wave functions psi and phi, and the product bracket psi times bracket phi. If we now switch the two bra vectors, we get two projections of psi on phi. These are either 1 if the wave functions are the same, or they are smaller than 1, so this new expression is smaller than or equal to the one before. This is an incarnation of the Cauchy-Schwarz inequality. Because any wave function can be written as a normalized function times the length, this also works for non-normalized functions like the one we have here. So now we have found a first inequality. Time to scrutinize the right-hand side further. The projection of delta A on delta B will give us a complex number. The absolute value of this number is smaller than or equal to the absolute value of its imaginary value, as you can easily verify. We can write it in terms of the original expression and its complex conjugate. And conjugating a projection is the same as switching the two wave functions. We can now plug in the definition for the auxiliary wave function again. Because A and B are both Hermitian, and because expectation values are numbers and hence commute with everything, many terms cancel out, such that all that we are left with in the end is the commutator of A and B. So here is Heisenberg's uncertainty principle in the most general form I know. The uncertainty of A times the uncertainty of B is always greater than or equal to the absolute value of 1/2 times the expectation value of the commutator of A and B with respect to the state psi of the system. If the commutator gives a number, this feels even more fundamental, because it can then be pulled out of the expectation value and the result becomes independent of the state of the system. This is, for example, the case for the position momentum uncertainty. You may encounter this relation with different values in the denominator. I think I've seen it with 1, 2, square root of 2 and 2 pi. This is because the notion of uncertainty is not well defined. Scaling this up or down will change the formula of the uncertainty principle. The fundamental result stays the same though. The more accurately you measure the value corresponding to one operator, the less accurate the values of all operators that do not commute with it become. Remember that in the last video we found that the ground state in the quantum mechanical oscillator has a non-vanishing energy of h bar omega over 2. Heisenberg explains this. If the energy was 0, then both kinetic and potential energy had to vanish. This means that the particle is lying motionless at the bottom of the potential, so we would know both its position and momentum exactly. That's not possible, so some uncertainty remains. Also note that this additional term of the zero-point energy only arose mathematically because position and momentum do not commute. For some more examples of how fundamental Heisenberg's uncertainty principle is, you'll have to wait for the next video. Until then, enjoy life if you can, and don't be ashamed if you can't.